Welcome back to a physics question of the day. In this video, we're going to be going over algebraic kinematics, some of the facts for it, and 3 different examples. So let's get into the facts. Alright, so our facts here, I'm not going to go through these one by one. They're going to be in the description down below, linked for the full kinematics fact sheet. You can also take a screenshot of these here, but we're going to be using these for acceleration and free fall. So when we do algebraic kinematics, it's going to apply to both horizontal kinematics and free fall as well. So again, just take a screenshot of these if you want to do that, or in the description down below, I will have the full kinematics fact sheet there to download. So moving into some of our equations here. All right, so these are algebraic kinematics steps. There's 4 steps here, including then which equation you're going to end up picking at the end of the day. The most important thing here, besides your equation obviously, is defining a positive direction. So this really becomes important when you have up and down values in here, and we're going to have a thrown upwards example in this video. So it's very important there which way you define positive and which way you define negative, because if you define, say, up as positive and down as negative, and I call my initial velocity upwards a negative number, I've screwed up the entire problem. So just keep with whatever sign you use. Typically, you make up positive, down negative, but sometimes it just makes it easier to make down negative if everything else is, down positive, my bad, if everything is in that direction, so you don't have to deal with negative numbers in your calculator and things like that, or negative numbers when you're dealing with the equation in general, because this is for AP Physics, you'll end up dealing with just variables when you do equations later on, so you don't want to mess up signs when you do stuff like that. Again, I'm not going to really explain this. Just take a screenshot of the facts here. This is what you're going to end up using, because I'll explain it in the context of the actual questions. So let's get into our first example. All right, so example number 1. We have a baseball dropped from the roof of a tall building. Takes 3.1 seconds to hit the ground. Part A, what is the magnitude, which means the amount or the number, and direction of the ball's acceleration immediately after it is dropped, and justify our answer. So again, how we justify answers here, we start off with a fact of physics from your fact sheet. You're then going to talk about kind of how this fact is going to apply, which is your reasoning, and then your claim, whatever your actual answer is. So if you have a ball here, and it is going to be dropped downwards. I don't have an example of this to show you on the slide, but a ball going downwards is going to increase its speed, because last time I checked, when I drop something, it gets faster as it goes downwards, and gravity is working down. So with this, the fact I'm going to start off with is on my acceleration facts. And I'm going to look at here, since my object is increasing speed downwards, when an object increases speed, its acceleration is in the direction of the motion. So that's going to be the first part of my evidence, reasoning, and claim. Then I'm going to talk about that this ball is moving downwards and increasing speed. So say something to the effect that the ball is dropped, increasing speed downwards. So if I'm increasing speed downwards, and that's the direction of my motion, then my acceleration is also going to be downwards. Then we're looking for the actual magnitude or amount of this. Any object that is thrown upwards or dropped is going to be in free fall, and that's where my free fall facts come in. Its vertical acceleration when an object is in free fall is 10 meters per second, or 10 meters, it gains 10 meters per second of speed every second, and that means that my acceleration is going to be 10 meters per second per second. So if I write this out here, or I have this typed out, what I'm going to have here is my full answer. So when an object increases speed, its acceleration is in the direction of the motion. That's my fact. That's my evidence. Then my reason, the ball is increasing its speed downward, so its acceleration is in the downward direction. When an object is in free fall, its vertical acceleration is always 10 meters per second. I'm then going to say when an object is thrown upwards or dropped, it's in free fall. So then we know that the magnitude of the acceleration is 10 meters per second So that's my whole justification for that. Again, something that's dropped downwards, its acceleration is always going to be down. We're going to talk about that in a second on another question where we throw something upwards. So then here, part B. Following the steps in a kinematics calculation, calculate how tall the building is. So that is going to use our kinematics chart here. So the first thing here, we're going to define a positive direction. So since we're working with everything going downwards, I'm going to make down positive in this situation. This just makes my life easier when having to plug negatives into the calculator. But you can make up positive and down negative. This will become important in the next example. So let's see here. I'm just going to say that down is going to be positive. All right, so if down is positive, then we're going to make up negative, and that is our first part here. So then with our kinematics chart here, or indicate the words, what motion we are considering. I'm not going to indicate this in words just for time's sake here and the space that I have in the slide, but we're just considering from the top of the building to the ground essentially. So that's just basically what the question's asking you here. And then now I'm going to make my kinematics chart. So my kinematics chart, what I am going to do is write out all my variables. So I have here v naught, that is my initial velocity. I have vf, that is my final velocity. I have acceleration. I have displacement. This can be in any order. I just switched the order between acceleration and displacement actually. And then we have here time on the bottom. So let's then look at our prompt on the top and see what we have here based on our situation. So the first thing I'm always going to have when an object is in free fall is my acceleration, which is 10 meters per second or 10 meters per second squared. Since I made down positive, I can just write this as positive 10 meters per second or 10 meters per second squared. What else do I have here? It says the ball is dropped from the roof. When something is dropped, it starts from rest. So this means that my initial velocity is going to be 0 meters per second. My final velocity, I don't see that quite yet. My displacement here, how tall the building is going to end up being, that is what I'm being told to calculate, so that's going to be my question mark. And then my time is given in the prompt here as 3.1 seconds. So we have everything here. We don't have final velocity, but we do have 3 out of the 5 variables, so we can use an equation. So final velocity doesn't really matter here. So we can use one of our kinematics equations. So I have initial velocity, I have acceleration, I have displacement, which is what I'm looking for, or the height, and then time. So with these 4 variables, I can look at my 3 equations and match up what I have here. And the equation I'm going to end up using is my displacement equation. So that's going to be here the change in x equals v naught times t plus 1/2 at squared. Anybody in Regents that happens to stumble upon this, it's the same exact equation as d equals vit plus 1/2 at squared, just with different notation, but the same exact idea. All right, so when we're going to plug this in now, my displacement is what I am looking for. What I'm going to do here is solve this algebraically first, but it actually seems to be solved algebraically. My first thing here, since my initial velocity is 0, anything multiplied by 0 is going to be 0, so v naught times t, that's going to be 0. So I'm going to be left with here, the change in x is going to be 1/2 at squared. And look at that, I don't have to do any crazy algebra because my isolated variable is already on one side of the equation by itself. So now we can just plug in numbers. So we're looking for our displacement, which is the change in x. Then we have over here 1/2 stays what it is. I can plug in my acceleration. That is going to be 10 meters per second. I'll just put squared here for space, but meters per second per second. And then my time is given to me here as 3.1 seconds. And always remember to square that. That's one of the biggest mistakes I see, is you go through everything with this and then you forget the squared value here. So now you can just plug this into your calculator and get your answer. So 3.1 raised to the second power times 5. That is going to give me a displacement here of 48.1 meters. So since this is positive, since I decided to make down positive, I can keep this as the height of my building because it gives me a positive number. So 48.1 meters is going to be my answer for the height of the building. So let's move into example number 2. Let's move into example number 2 here. We have a 0.25 kilogram baseball. It's thrown upward with a speed of 30 meters per second. So we want to find the magnitude or the amount of the acceleration along with the direction of the ball's acceleration after it is thrown upwards, and we are going to justify our answer. We'll also then going to get the approximate maximum height through a kinematics calculation. So in part A, whenever you throw something upwards, it is going to be also free fall, because once it has left my hand, the only thing that's working on it is going to be gravity, because we're not going to deal with air resistance in here. So with this, what I'm going to do here is the direction of the ball's acceleration first, because when I throw something upwards, it is going to eventually come to a stop at its highest point, and that is going to be actually one of our free fall facts, and that is going to drop back into our hand or to wherever it came from. So since we are throwing something upwards in the upward direction, starts off with that motion, is then going to slow down to 0 at that point. That's the max height. That's all we're worrying about at this moment. So upward motion, slowing down or a decrease in speed. So that means that my acceleration should be downwards. So our fact here that we're going to use when an object decreases speed, its acceleration is opposite the direction of the motion. Then we explain that we are moving upwards initially, slowing down or decreasing our speed. So since we're moving upwards, our acceleration is going to be then downwards. Then for the actual number here, we are going to look at our fact sheet for this as well. So I know as well anything that's thrown up or dropped is going to be in free fall, and I'm actually going to add this to the fact sheet as well in the free fall section. So anything that is thrown upward or dropped counts as free fall. So then I can end up using the facts for free fall here. So with this, I'm going to use the fact that it's when an object is in free fall, its vertical acceleration is always 10 meters per second per second. So that's my fact. I can then say that I know that it is when something is thrown upwards or dropped, it's in free fall. So then my acceleration is going to be 10 meters per second every second. So we can have this typed out here. So when an object decreases speed, its acceleration is in the opposite the direction of motion. So with throwing it upwards, we have a decrease in speed while moving upward, so its acceleration is in the downward direction. Then we have when an object is in free fall, its vertical acceleration is always 10 meters per second per second. We know that any object dropped or thrown upwards is going to be in free fall, so its magnitude of acceleration is 10 meters per second, or 10 meters per second squared. So now we're going to do in part B here a kinematics calculation. So we do this again. We want to start off with defining a positive direction. So for this, my positive direction, I'm just going to call this up because I'm throwing it upwards. This is where this really becomes important because I have an upwards velocity and a acceleration in the opposite direction. So we're going to call up positive and we're going to call down negative. So now we can make our kinematics chart. So let's write this out here. We have V naught, that is my initial velocity. We have Vf, that is my final velocity. we have our displacement change in x here, we have our acceleration a, and my time for the motion t. So now let's look at our prompt and see what we have here. So we have a 0.25 kilogram baseball. Mass is not going to matter. I'm going to do that demonstration at one point. We throw it upwards with a speed of 30 meters per second. So my initial velocity here is going to be 30 meters per second. So that is going to be v naught. Then we're going to have my final velocity. That is a fact on the fact sheet. Its velocity speed when in free fall will be 0 meters per second at the maximum height. Since we're only working to the maximum height, that's going to be essentially our motion that we're considering. We're only working from thrown upwards to the max height. So my final velocity can be 0 meters per second. Then we have here the change in x, or my displacement. I'm trying to find the max height, so that is going to end up being what I'm looking for. So that's my question mark. My acceleration we have here in the first part, that is going to be 10 meters per second per second. So we're going to put here 10 meters per second per second. And since we made down negative, this will be a negative number. And then time, we already have 3 out of the 4 variables, so we are not going to end up needing time in this situation. All right, so now we can figure out an equation that is going to use these 4 variables and is going to find me my displacement. Since we do not have time, that is going to lend me to the timeless equation. So I'm going to write this out here. Vf squared equals v naught squared plus 2a change in x. So this equation is the same one for Regents, just with different notation again. So for my Regents students who are also watching this, if you want your extra help on it, it's the same exact equation. V naught is vi, and the change in x is d, but still does the same thing. So now again, what I'm going to do here is solve for my displacement algebraically, and then plug in with my numbers. Since my final velocity is 0, I can get rid of vf squared. That's 0. So I'm going to have here 0 is equal to v naught squared plus 2a change in x. So since I have my initial velocity squared attached to my displacement with 2a by a positive or addition, I'm going to end up doing the opposite of this and subtract out v naught squared from both sides of the equation. So I should have here on the left side negative v naught squared is then going to be equal to 2a times the change in x, or my displacement. So I'm going to do this next step all at once here so we don't run out of room. So 2a times my displacement, multiplication there attached by, so we do the opposite operation and divide out 2a from both sides. And now we have isolated my displacement on both sides, on the right side of the equation, my bad. So I should have here negative, and that's going to be on the outside of the parentheses essentially for v naught squared, over 2a is going to be equal to my displacement. So now I can plug in my numbers. So we're going to have here negative and put inside the parentheses my v naught. That is going to be 30 meters per second. And that is raised to the second power, all over 2 times negative 10 meters per second per second. So we're then going to plug this into my calculator here. So you should have a negative over a negative giving me a positive since we're going upwards here. So you have here 30 raised to the second. That's going to be 900. Again, the negative is outside the parentheses because I have here just my velocity is being squared. My negative is going to be not going to be squared because it's not in parentheses initially. And then you have there on the bottom 2 times negative 10, and that's going to obviously be 20. So 900 divided by 20, should give me an answer of 45 meters. If you end up with a negative number, just recognize that there was some kind of math error there, but it's not the end of the world as long as you can understand that you're going upwards and height is going to be a positive number if you're trying to get height here. So we should have here that the change in x, or my height, is going to be 45 meters. So let's move into our last example. All right, so our last example here, the speed of a wagon increases from 2.5 meters per second to 9 meters per second in 3 seconds as it accelerates uniformly down a hill. Our first part here again, but it's a little bit different from the previous two. What is the direction of the wagon's acceleration as it moves down the hill, and justify your answer. The reason why it's only a direction here, this is a object moving along a hill. So think about like the cart on a track here. It is not being thrown upwards, it is not being dropped, so it's not in free fall. So we're not going to have the magnitude of the acceleration unless we do the math for it. It's not a fact, so we're just going to find the direction of the acceleration straight away. And then part B, as we have been following the steps in kinematics calculations, find the acceleration of the wagon during the time interval presented. All right, so part A. What is the direction of the wagon's acceleration as it moves down the hill, and justify my answer. So again, we're going to start with a fact of physics. As always, that's going to be our evidence. We're going to explain that fact a little bit and then make our claim, which is our answer here. All right, so based on this, it tells me in the prompt the speed of the wagon increases from 2.5 meters per second to 9 meters per second as it accelerates down a hill. Uniformly just means the same acceleration all the way through. So since we are moving down the hill and we are getting faster or increasing our speed, we can use the fact here when an object increases speed, its acceleration is in the direction of motion. So we can use that fact to start off then. We're then going to say, since the wagon is increasing its speed down the hill, my acceleration will also be down the hill. So that should be our answer that I have typed out here. When an object increases speed, its acceleration is in the direction of motion. The wagon is increasing its speed down the hill, so its acceleration is also down the hill. Acceleration is in the direction of the motion when I increase speed. So perfect. Our last part here, following the steps in a kinematics calculation, find the acceleration of the wagon during the time interval presented. All right, so with this, we are going to be able to write out our kinematics chart. First off here, we're going to make a positive direction and a negative direction. I'm just going to make positive down the hill. So we're going to say down the hill is going to be positive here. It's going to be positive, and up the hill will be then negative. And we are considering the motion of that 3 seconds because it says during the time interval presented. We're considering that motion when I increase my speed from 2.5 meters per second to 9 meters per second, those 3 seconds there. So let's just write our kinematics chart now. So I have here V naught, that is my initial velocity. I have here Vf, that is my final velocity. My displacement is going to be the change in x. My acceleration is what I am looking for, and then t is going to be the time interval for the motion to happen. All right, so we have here V naught, which is the same thing as Vi for my Regents students. V naught is my initial velocity. It says that the speed of my wagon increases from 2.5 meters per second. That's my initial velocity. Then it goes to 9 meters per second. So that's my final velocity. It's right as 9. Don't need to write out 9.0. My displacement, it doesn't give me here, so we're going to wait on that. My acceleration is what I'm trying to find, so that is going to be my question mark. And then my time, it tells me, is going to be 3 seconds. So since we have 3 out of the 5 variables, I don't need to have then my displacement here, so we can just get rid of that. And we have enough to use one of the kinematics equations. So we have the initial velocity, the final velocity, we have the time, and we're trying to find the acceleration. All right, so the equation we can use based on this is going to end up being my final velocity equation. So I can put here that Vf equals V naught plus AT. All right, so again, I want to start this off here with solving for my acceleration algebraically first, and then plugging in. So with this, what I'm going to do, I have V naught plus AT. So my initial velocity is attached to A times T by addition. So I'll do the opposite of this and subtract V naught from both sides of the equation. So I'm going to have over here Vf minus V naught, or Vf minus Vi, is then going to be equal to acceleration times time. So the last part here, I have acceleration times time. I want the acceleration by itself. So I'm then going to divide out time, since it is attached to acceleration, by multiplication. So again, do the opposite operation. So I have here Vf minus V naught over time is going to be equal to my acceleration. So now I can plug everything in. So I have here 9 meters per second minus 2.5 meters per second all over my time, which is 3 seconds, is equal to acceleration. I'm not going to go through all the math steps here, so just plug this into your calculator. So we have here 9 minus 2.5. So you should have 6.5 meters per second on top, divided by 3 seconds on the bottom. So you should end up with an answer here for your acceleration as 2.2. Let me fix that. 2.2 meters per second per second. And that is going to be my answer. So again, we made everything positive here, since going down the hill was positive. Otherwise, we would have had all negative numbers and it would have been weird. So since we were going down the hill, I made everything positive. So when we plug everything in, 9 minus 2.5 over 3 should give me 2.2 meters per second per second. So it's gaining 2.2 meters per second every second of motion, or just 2.2 meters per second squared is also fine. So hope you found this explanation helpful, and see you guys in class.